we will go ahead and get started. Thank you to everyone who joined us in the room and online for airtime. This is a seminar presented on the NAMS-2 contract, that is NASA's academic mission services. So we have partnered with the Citrus Institute to give a series of seminars. Let me get this on screen for everyone in person here. And here we go. So today we have with us Dr. Chen, who earned his PhD from Nanyang Technological University in Singapore. He has been a faculty of electrical engineering at Utah State University up until 2012, and then joined the School of Engineering at the University of California, Merced. He has been teaching undergraduates and graduate students, and his research interests include mechatronics for sustainability, cognitive process control, small multi-UAV-based cooperative multispectral personal remote sensing, applied fractional calculus and controls, modeling complex signal processing, distributed measurement and control of distributed parameter systems with mobile actuator and sensor networks. He is listed as highly cited researchers by Claritative Analytics from 2018 to 2021. So we give a warm welcome to Dr. Chen.
Thank you for your introduction. Thank you very much. This is a great opportunity to share some of our work on this field related to the UAV. So let me first start by, where's my screen? Okay, it's here. Okay, let's see. Okay, first of all, I want to thank Crown Innovation Incorporation, NASA AMS, and the UC Citrus, especially Julia, and she coordinated the scheduling of this presentation. I want to thank all for my former PhD students, especially Dr. Rafi Shishak. He graduated last November. Thank you all for coming. So basically, this is a paper we presented last November in Paris. Exact the same title, but I feel this is boring just to show you this paper. And I'm not sure everybody is interested in the fire problem. So I want to show you a chain of thoughts on how this idea was from. And so I'm going to share with you the chain of the thinking over the years that led to do this piece of work. So my plan today is first to do some introduction about myself, my lab at the UC Merced, and drones, and some of the thinking in the drones. I think lots of people here are interested in the drones, especially the drones in the recent months. We have seen it in action in wartime. After that, I'm going to present what is a DPS CPS framework. And today we are in this in the AI age. We are in the time that we have more sensors, more actuators than really needed. I call it sensor and actuator rich systems. Then after that, I narrow down to the fire problem. Basically, I give you a quick tour of what's in this paper. After that, I'm going to introduce our future opportunities. So my goal of my presentation today is to stimulate thinking just beyond the fire problem. So about myself, there's a very interesting picture here. In 1996, 40 years ago, maybe 30 years ago. 30 years ago, there's a guy published a paper in Nature, maybe Science, about putting a GPS tag on albatross to plot its foraging behavior, how they seek food. It turns out the flight trajectory is like A and B. This is called leeway flights. I draw an analogy to a human life trajectory. So you need to make leeway flights. By the way, Levy flights is a fractional order stochastic process instead of integer order stochastics. The integer order random search is called Brownian motion. But for all the birds, using that Brownian motion integer order calculus strategy to seek food, they're all distinct. For those survived, they must use fractional order searching strategies. So all the birds already learned fractional calculus. So that's one of my 5 major research interests. So you can see I geographically, I stayed in Beijing, then moved to Xi'an. For those who do not know where's the Xi'an, probably you know this is the starting point of the Silk Road in the Tang Dynasty. Then I moved to Singapore for my PhD, and at the same time, I also worked in the industry for disk drive solve a problem. So most likely, your disk drives, if it is manufactured by Seagate, it is still running my algorithms there. Then I moved to Utah State. Then in 2002, I get into the tenure track. After 10 years of tenure track, and then I moved to California, UC Merced. And it's in the Utah State, I developed a very dedicated research interest in the MassNet, so mobile actuator and sensor networks. So I have a group of actuators and a group of sensors. They talk to each other and collectively do something meaningful. For example, firefighting. And in the University of California, I developed new interest in digital twins, especially for the agricultural drones, environmental monitoring drones. And most recent 5 years on machine learning that respects the complexity, not just physics. So it's my life trajectory as a Levy flights. So this is one slide, that's about myself. This is one slide about my lab. So basically, as a professor, we have only 3 jobs to do, teaching, service, and research. Teaching, I develop this amount of courses. In a nutshell, you can see I'm basically a control guy, and I want to put things under control whenever it's controllable, okay? We don't want to control something that is not controllable. So for lots of service work, outreach, and our research is mainly on UAVs, and I coined the term called personal remote sensing, PRS, because the drone is at this level. Today is very correct. I think this term I coined in 2005, 21 years ago. And cyber physics systems and mechatronics, applied fractional calculus. I also do renewable energy system, but modeling control. So our funded efforts are mainly on 3 or 4 areas: energy related, water resource related, and precision ag environmental monitoring related. And most recently, I also did something on the digital heritage. That is using a drone for 3D mapping of historic sites or objects. So I have hosted hundreds of over 100 visiting scholars. Most of them are visiting me is because of fractional calculus. And also had more than 200 undergraduate students gained research experience in my lab, and graduated maybe now around 20 PhD students. In a nutshell, my lab is a mechatronics lab. So mechatronics is a very interesting intersection of 4 areas like mechanic systems, control systems, electronics, and computers. So I want to say today the AI is going to like physical AI, but to me it's actually a mechatronics. So okay, drones. Why I do this? Let me see. Why this is not working? I'm sorry, give me a second, okay? Let me see if I can get it to work. So I forgot where I got this video. People are talking about drones in different purposes. Today, we can say that the applications of drones are only limited by our imagination. So, and especially when you have more than one in the team, like swarming. So drones, in a nutshell, we have three broad categories, like drone used as a sensor. And so, for example, personal remote sensing, I suggested in 2005. Remember that we put personal in front of remote sensing. We're going to have a revolutionary job market. For example, we put personal in front of computer in the 1950s, 60s. So we produced Steve Jobs. We produced Microsoft. So we put personal in front of remote sensing. You can imagine we have a next gen of Steve Jobs. Second is the drones used an actuator. So use the drones to apply something. It's also called drone applications. So when I say drone applications, it's not just applications of drones. The drone application is use the drone to apply something, serving as an actuator in changed situation. So it's less discussed. You can imagine a lot of things like flying hammer and you can flying screwdriver. It's all possible, right? So, and the third broad category of the drone use is on the mobility platform. What flying cars, flying pickup trucks, and flying ambulance, flying taxi, and so on and so forth. I know that many of you are interested in the UAM. Especially NASA has been working on this one for a long time. I know PK is a leading figure on that. So how to manage the traffic. But on the other hand, people also can say, oh, do we have like drone as soldiers and drone as firefighters and drone as fire starters, like a flying igniter or flying lighter and spies and so on and so forth. But I think it's safe to say drones can be used as three categories: sensor, actuator, and mobility platform, or a combination of them. Okay. So let me walk you through briefly a drone as an actuator. I go very quickly and say, for example, in the aero manipulation, like force exertion, pick and place, and assembly. And you have environmental intervention and spray something like a crop duster. To me, it's a drone actuator. Okay. And of course, you spray a fire retardant. It's also a actuator, right? There are also something interesting like cloud seeding to make rain, and so on and so forth. Infrastructure maintenance, like using contact-based inspection. So you use a flying hammer to knock and hear and see the sound is something abnormal or not, and so on and so forth. Repair and coating, you spray as painting, hot rich joints, apply some anti-corrosive sealants. And communication energy, you know, the dynamic relay to have a communication relay network. You can also use drone for the WPT to like fueling aircraft, right? So emergency response, like AED delivery and or live buoy, active lighting. So you use drone to light. Physical interactions, protein docking, and haptic interaction. and lots of applications, drone as actuators. So it's a very broad topic, in fact. So I do have a video, maybe I think it's very, very, very short regarding flying igniter. I think you can.
One of the most dangerous things that we can do is go inside the burn unit as it's actively burning to put
Only
more
40 seconds.
We have integrated drones into our work, both for monitoring and increasing our situational awareness while the fire is going on, but also accomplishing that interior ignition without putting firefighters at risk.
A prescribed fire is a lot different from a wildfire. It's very carefully planned. All kinds of variables are thought about in advance. So it's the planned use of fire to accomplish a set goal or objective.
The ignition drones allow us to do more work, putting more good fire on the ground where it needs to go with the same amount of resources or less than we have now.
Okay, so we got a taste of my scope in here, and we use drones for sensors and actuators. Of course, we are focusing on the fire problem, but it could also be other problems. Okay, so in that sense, it's a very good idea to review this DPS CPS framework. Hopefully, this can broaden our view about the use of drones. So what is DPS? What is CPS? Let me spell out. DPS stands for distributed parameter system, like fire, the methane emission, the pollution diffusion, even the vibrating bridges, and so on and so forth. In other words, this dynamics is governed by a partial differential equation. The system dynamics evolve not only over time, but also over spatial variables. Okay. So clearly, I'm going to imply that the fire-related problems is a DPS plus CPS. And I think a lot of people know what is a CPS, cyber physics system. And it's just like the same analogy saying that you are not yourself alone, and you are yourself plus your information footage. Sorry, footprints. The same thing is true in the future. A physical system is hard to separate from its cyber supporting system. So there is no hard line to draw between cyber versus physical. It will be intimately merged in the future. So this term is popularized by the NSF since 2018. Okay, 2018. Oh, no. 2008. I'm sorry, 2008. Okay, 2008. Oh, let me go back to textbook. You see that this is a typical textbook on signal and systems. This is a very popular signal and linear system textbook by Lethe, very famous name. We use these textbooks. I'm trying to tell you that the title of this book should be 2 lines underneath in here. Should be 2 lines. You can read it. I'm going to put a table in here. So when we talk about a signal or talk about linear system or systems, so we can say linear, nonlinear, time invariant versus time varying, and so on and so forth. Finite dimensional versus that, deterministic versus stochastic, continuous time versus discrete time, and so on and so forth. There's also a lumped parameter system versus distributed parameter system. So one is by ODE, one is by PDE. One is only a time evolution, one is a temporal and spatial evolution. So I think the fire problem is distributed parameter system here. You cannot ignore the spatial variable. There are many other attributes about systems and so on and so forth. One of that is called integer order versus fractional order, meaning the differentiation order should not be just integers, first order, second order. It could be 1.5's order and so on and so forth. that's the area of my interest. Okay. So in a nutshell, this whole system, the textbook title should be 2 lines long, like 2 lines long. You have a lot of limitations put in front of it. Okay. So I just give you an impression that we really need to pay attention to what we talk about the or fire problems. Is could be all on this column. Okay, put on this column. So what I'm trying to talk is we know that there's a period of time very fashionable to add computation in front of almost everything. So, but I would say that this is true, and we need a model so predict the performance or behavior. But sometimes this behavior should be under control. So I said control could be put on after almost everything that is controllable. So you just can go through whatever you can, like aging, your diet, weight control, and so on and so forth. Of course, we can also add fire, or we can say fire control. But fire control is actually a different name in the military. Fire control means how you shoot accurately. So anyway, so with that comes to the CPS, cyber physics system. You need computational thinking, meaning you need a model. You need a control thinking, that closed loop. You always ask, when you measure something, then for what? Who will use it? And eventually, your loop is closed. So it's basically saying that computational thinking and the integration of this computation around the physical system, it's called a cyber physics system. So there's always a bigger closed loop, okay, with those sensing, decision, actuation, computing, networking, physical processes are mixed. So the fire spreading problem is one of the physical processes. So this is a more general discussion, just to imply that EPS and the CPS describes the fire problem. So the common attributes of the CPS, it has a closed loop picture already explained. And they are PDE, spatial temporal, and they are distributed primary systems. So with that, yeah, this is actually a drone. It's a drone spreading of pests. So you have spatial temporal and spreading of the locusts is a very dynamic. So this type of control problem, you need a sensor and actuator rich problem. And using the human as a mobile actuator is not enough. Anyway, so just give you a feeling. So it has to be using a mobile actuator, and mobile sensor and talk to each other. So in the precision ag, so you have a drone and serving as a remote sensing platform to understand the soil moisture and the crop health, and then pests condition, and you have a crop duster, you spray on pesticides. Also, you can spray on the leaf and fertilizers, okay? But the question is where and how much you apply and when. These are the very important control cyber physics system control problem. So the same thing is like crowd control. So you also have the same problem and the spreading of the crowds and how to put enough sensors and enough actuators. Here, actuators are just police person or some infrastructure design to manage the traffic, okay? And harmful algal bloom is another cyber physics system, is a spatial temporal. we really need to understand the spreading as well. And this algal bloom research, you have remote sensing, you have mobile sensor, you have mobile actuator to apply the chemicals and to understand how to apply and where and how much and when, and so on and so forth. Having those both as mobile actuator. Now comes to the fire. So you can imagine that we need the similar philosophy using mobile sensors and mobile actuators, right? So this is very logical. We put this one into DPS thinking, into CPS thinking, DPS plus CPS, okay? So yeah, of course, it's a very difficult problem. You have wind, you have non-uniform humidity, and so this wildfire control scenario is actually distributed parameter control systems. So that's naturally we ask a question about first how to measure, and the same thing applies to how to actuate, how to control. It's not really as simple as straightforward. Before we need to answer the question in this DPS system. So you have sensors where and what to measure, why measure, and who to measure, where to measure, when to measure, and how to measure. So in the abstract setting that you have domain of interest omega. So your sensor could be only like boundary sensor. You cannot go inside. You only can measure the boundary. You have point sensor. Okay, so you have filament sensor, you have line, and you have a subdomain or a regional sensor. It's called regional. Okay, of course, if your field of view is large enough, you have a whole domain sensor. Okay, but usually it's not true. The capital omega is very big. Your sensor footprint is only limited. So you have to piece information together to fuse them. It's called image stitching, right? So from that perspective, we have 5 different zones of effectiveness of the sensor. I said point-wise, you have zone sensor, domain, whole domain distributed, filament, or boundary. You have 5 of that. And you also have actuator could also be the 5 types. And the sensors actuators could be static or mobile. So for a given a DPS, distributed parameter system, your sensor actuator configurations, you will have, I put here 5 by 5 by 2 by 2. So it's 100 cases, okay? 100 different combinations. But you should say that the sensors actuators are put on the same mobility platform. So on the same robot or same drone, you have both sensors actuators. I call this is collocated. And it could be the drone, one drone for sensor, one drone for actuator is called non-collocated. So you have 2 more cases, okay? And also you have other cases like sensor to actuator, actuator to sensor, actuator to actuator, and sensor to sensor. The communication topology and configuration is 4 times. So for any given distributed parameter system, you should have this 800 different configurations. I think each configuration could graduate 1 PhD student. So we can have 800 different topics for PhDs. On the other hand, some of the sensors are fixed. Say, for example, Golden Gate Bridge, you have many sensors there already monitoring. But sometimes you consider you scanning the sensors, so you don't have to be on all the time. You rotate. So that kind of scanning sensor of fixed location sensors is also considered as a mobile sensors. The same thing is true for the actuators. So you may wonder on the Golden Gate, bridge, what are the actuators? So the bridge is vibrating, and you have cars moving on top. That car is actually moving actuators, okay, on the system. Yeah, it's very simple. The room you're sitting in is one of the 800 configurations. You have a static sensor, thermostat, which is pointwise, and you have actuators, maybe more than one, those vents, okay? And they are usually at different places put, so it's non-collocated. So this is just one of the examples. And in 2002, we started to work on this configuration. Remember, in 2001, we had 9/11. So therefore, we're talking about somebody putting a toxic gas, okay, polluting area. So we need to have a mobile sensor to understand where are the evolving fronts. Then we put mobile actuators to spray and neutralize that toxic gas plume. So then we can contain it. So this thing is called mobile actuator and sensor networks. It's a distributed parameter system control point of view. Along this line, under this picture, we graduated many, I think safely we can see over 10 students on this topic on different areas. And also, this is the reason I moved to California. In Utah, we have almost 6 months of snow coverage. So you fly the drone, you don't see much except the snows. So California is the right place to do the precision agriculture using drones as a moving sensor. So and it's eventually a closed loop problem on how you can do irrigation control to maintain the crop moisture level, so that you use the water on the triple R. I call it right time, right place, and right amount. So I call this the Water Watch research program. That started in 2005. In 2004, we at that time we don't have this. Today we have XB type of embedded communication so that the robots can talk to each other easily. At that time we have Zigbee, not pre-Zigbee. So we are among the first to use the crossbow chipset CC100 to make the embedded communication possible. So the robots can exchange the information. So we build a platform, putting a stage fog generator and have a cover underneath the cover. We use the drones to moving collaboratively so that we can encircle this dynamic evolving boundary by using underneath we have an optic sensor to do the detection. So that's called mode. At that time, it's called mode-based distributed robot for plume tracking test bed. So we drove to Berkeley and got the second place of the Smart Dust Challenge, 2005. So this type of work is you can roughly consider this is a fire spread, right? It's the same problem, isn't it? So we started to do this type of work very early, and yeah, we produced a huge amount of research outputs. So let me see some of the stuff here. And so that's 2006-ish. We produced the GUI, produced everything. This is called formation and tracking. So I call this as a VIP. These are 3 robots are bodyguards. If you go somewhere, then bodyguard will always surround you. And this one is like a rendezvous, and we have rendezvous on the line. So without centralized control, so only by exchanging information between the individual agent. And so that 2006, 2007 time window, these are produced from our research platform we constructed. So again, I hope this type of smart sniffing and smart spraying problem is directly applicable to the fire problem. So we also did simulation platform, and so these are sensor networks, and they're moving. So there's a diffusion source. Imagine this is a fire and spreading, or a pollution source. So then we have blue circles are mobile actuators to spray, neutralize the diffusion, the pollution source. Of course, spraying neutralized chemical in amount proportional to concentration in the region. So what we come out is a Voronoi tessellations idea, so that each robot will work on their problems without colliding each other, because they live in a different Voronoi cell. Okay, so the obstacle avoidance between the mobile actuators are automatically built in. And the method is also very scalable. If you have many of them, you don't cluster in one place. You just like divide and conquer automatically, autonomously. So this is XY in the 1x1 region. 1x1 region. And you can have multiple sources, and in the fire problem, so we cannot always assume you only have one hot spot, right? So you may have more than one. And then we also assume that the source is moving. Some bad guy put on the pollution source on the truck. So this is also doable for moving and contaminated sources. And we also assume we can have somebody on some obstacle, dangerous entity moving, so we can avoid it by using this potential field concept. And we introduce the fraction order potential field. We can introduce the tuning knob called the danger, degree of danger, so that the obstacle avoidance behavior will be different to the different level of danger. So that kind of concepts just gave you an idea. So in summary, we treat this DPS control in one of the 800 configurations. Then start to think about sensors, actuators are both movable, and how to best moving them along the optimal path, how to systematically discuss it. So it's summarized in this book, 2012. In the cyber physics system, how we can make optimal observation, and so that always you get the most interesting and valuable information back. So you don't want to stay sensing in the area that doesn't contain lots of interesting information. So there's something called Fisher information metric-based approach, so that you move your sensor to the right place with good justification, with mathematical justification. And same thing applies to when you have moving actuators. This book is mainly on observation. This book with actuation. Okay. So just to give you a taste of our previous work. So, okay, my time. Okay, my time is good. So I'm going to make a very quick. So at this point, I hope you agree that the fire problem is a DPS CPS problem. It potentially is a sensor actuator rich system. Okay, so then how we can move them, use them, place them needs careful systematic thinking. So this paper, my student Rafi and presented in person in Paris, ICCMA. It's a mechatronics conference. So I'm going to give you a very quick tour of this ICCMA paper, and the DOI of the paper is here. By the way, I'm going to share the slides if any of you are interested, so you can download and click on this link. So quickly, I'm going to go through motivation and problem gap, digital twin framework, physics-based modeling, UAV sensing and control, and some results. The details is in the paper. You can check it. So I just gave you a quick idea. So of course, very important. The key problem is how you can use remote sensing to make a fuel reduction recommendation, so that you can do this actuation, meaning removing, burning those fuels, so that we can reduce the fire risk. Okay. So the traditional intuition-based control may not always work, so we really need a good framework. The reason it's a hard problem is fire dynamics is very nonlinear. You have a fuel amount and wind and the terrain condition, and real-time observability sometimes will be missing, and the human-in-the-loop constraints. And the key idea in this paper is to suggest a framework, unify this modeling, sensing, and control as a closed-loop problem, treated as a CPS agent, then build a digital twin and have a real-time decision-making suggestion. So the system architecture is like you have a wind model, reaction diffusion fire model, UAV sensing, and using thermal and multispectral, and actuation, then retardant deployment. So digital twin concept, we physics-based fire dynamics model, and it's a virtual replica, and this model is corrected in a real time through the real-time sense data. It's called continuously updated, okay? So this one will enable predictive and adaptive control. There are some math in the paper about the safety and wind modeling. And there's a solver we decided to follow using a 4-step solver, and to capture realistic wind transport, then fire propagation, the spreading dynamics, follow the reaction diffusion, consider the energy and the species conservation, and Arrhenius type of combustion. So this is a list of the models we surveyed. I think we can skip this one. It's actually well documented in Dr. Sheshak's PhD dissertation. So in our UC, we have online library. Okay, so also fire-wind coupling modeling is wind affects heat transport, the coupling through the convection term. So this part must be also considered in the model. And how we can do initialization, we rely on the two indices like normalized difference moisture index, live fuel moisture content, to estimation. And we can map out the fuel heterogeneity. And after that, we can, we can build a sensing processing pipeline, and we can extract the fire line through this remote sensing imageries. and fire region segmentation. Then we understand where is the apex, fire line apex detection. So the represents fastest spread direction. Then we know where are the priorities should be. For geometric tracking, the spline fit to these fire lines, to making the vector estimation on the tangent, so that we can decide the motion direction of our actuators to release the fire retardant. The control strategies, I call bread and butter, is always start with a PID. Then you try advanced control. Tracks target behind apex, ensure safety and observability. You can get data, meaningful data. Then controller, you define the area of the orthogonal to the fire line. Then you can do the velocity command through the PID. Then you have adaptive response to fire dynamics this way. So then UAV as actuator, you have fire retardant placement dropping, direct intervention capabilities, and of course we need to set up artificial potential field so that we avoid obstacles and fire breaks, using a gradient descent navigation. Fire redirection strategy, steer away from the targets, obstacle and placement, energy efficient. You don't want to stack on the same place for too long, and so on and so forth. Depending on where you want to redirect the fire to. So we did the 2.5 kilometer domain and a square kilometer domain, using a single ignition source, using a realistic wind boundary condition. You have with UAV intervention or without intervention, you can evaluate the spread and the intensity. That's all in the figure in the paper. So fire line can be redirected. You can reduce the intensity of the protected zone and slow down the spread. Okay, my time's almost up. So control can reshape the fire dynamics, not just to suppress, but also you can steer to make the fire to which direction, okay? So we suggest this new paradigm in the fire management. System advantages is the CPS, DPS thinking. We have a real-time adaptability, reduce human risk, scalable to the swarm system. You have more than one sensors, more than one actuator, so you can still work under this framework. Yeah, we only did 2D combustion, and we haven't considered lots of sensor noise, computation load, and there's a trade-off. But with the GPU and embed edge computing, we don't need to worry too much about computation here. Future work, multi-UAV swarming, and then we make evaluation of uncertainty quantification, and hopefully we have funding to do field validation. So this whole study is not funded. It's just part of the last chapter in my PhD student, Dr. Shishak's PhD dissertation last phase. So the big picture is we can get towards the autonomous wildfire management and the AI control plus physics, using the digital twin as the core paradigm. So I did some literature review. People are already thinking towards this direction. I find out the drone swarm in fire suppression is a concept framework. So future opportunities I want to share with you. I discovered a LinkedIn page talking about this drone fire suppression business is a multi-billion-dollar market, climate resilience, insurance mitigation, and fire defense infrastructure, not reactive, but all preventative and on speed to suppress. So he basically lists the three suppression directions we need to do in the future. We need to have a universal payload and a recharge system. We need to have innovative retardants for drones, and the private sector driving the fire suppression as a service. I want to add a number 4, that's math. So we need the equations. And of course, we need AI machine learning, but to me, they are just the math, okay? So that's the picture from that link. They use drones to combat the wildfires, but this is mainly for the actuation side. So the future opportunities, of course, a lot. I want to, okay, 3 minutes. Remind you that we have 800 possibilities, okay? But let me remind you that there are actually more, meaning we can consider if the process spreading is integer order or fractional order. The controller itself can be a fractional order. So then we have 4 opportunities, 4 combinations. So then controller can be regional or not. Observer can be regional or not. Regional means you don't have to put your control or observer or with the whole domain image. So information, you can be regional. So I think we started a new field. It's called regional analysis for those spreading processes, especially when it is fractional order. So in 2017, in France, we did a half-day workshop tutorial on regional analysis for distributed pyramid system. So instead of consider the capital omega the domain of interest, and actuator sensors are always happening at the regional small omega level. So then we need to add times 4 times 4, so it's 16. So then we have 12,800 cases. You can graduate this amount of PhD with those. So this book will be very interesting if you are interested in regional analysis. Instead of consider capital omega, you have small omega subdomain. Of course, I learned a lot from reading NASA's work. So they have this is 2021 drone application for wildfires. Again, here application, I mean you apply something, okay? It's actuator. It's not applications of drones. It's drone application. There's a difference. So in that talk, they talked about very important thing. It's called innovative fire retardant. And they mentioned about the fast fire knockdown. You have small region, you have fire I want to knock down. So there's something called non-toxic retardant. I'm so impressed by this work because you cannot apply something that is harmful to environment. You know, you need to have a lot of work. So I would like to say, so my time's up. So my time is good. Thank you for attending my talk. And so I stop here to see if you have any other questions. Yeah.
Dr. Chen, your timing is impeccable. Thank you so much for the presentation. We do open it up for conversation the last 5 minutes here.
Sure.
Hey, this is Tom. Just one quick comment. Thank you for the presentation, Dr. Chen. I'm going to paste an email address in the chat for
Yes.
another professor at Ohio State that seems like he's working on similar problems that I got a briefing from recently. I think maybe there'll be an opportunity for you guys to talk and collaborate. Okay.
Yeah, thank you very much. And I have an email address in here. Oh yes, Kumar. I think I have, yeah, I cut paste. I saved this one. Okay, thank you for the connection. I'll follow up. But I have zero funding on this fire related problem so far. I'm hoping have an opportunity to work with some funded efforts.
Yeah, I think I think Dr. Kumar might have some funding from NSF, but maybe you guys can talk and figure out a way to team up or something.
Sure. I'm too old to get NSF funding, and they cut this year again. So I'll leave this opportunity to young people. Okay, why my camera is off? Okay, sorry. I should be off.
Yeah, no problem. You can reference me, Tom Davis from Crown.
Okay, Tom Davis. Thank you very much, Tom. Yeah,
Yeah.
Tom Davis. Yeah. Let me write down. Okay. So really
right.
doing a lot of work on this firefighting problem. But I'm not sure who is exactly doing this DPS CPS framework. Yeah, and digital twin. Yeah.
Right. Other questions?
Well, thank you so much, Dr. Chen, for joining us today. We do appreciate your time. And
Sure.
to all of our guests who joined us in the room and online, we'll say airtime is taking a little spring break next week, so we will be back online on April 28th, another Tuesday at 11 a.m. We will be hearing from Professor Khan on his title From Autonomous Systems to Epistystemically Aligned Human AI Teams for Advanced Air Mobility. So we will see you all then. We will put a feedback form in the chat, and there is a QR code at the back door. Who are with me in person, we do appreciate feedback wherever possible, and please have some coffee on your way out, and everyone have a wonderful day.
Thank you very much for your time. Yeah.
Thank you. Thank
Bye-bye.
you.